So the last presenter for today is Yunglong Luo, and he will be talking on the culture of cyanobacteria and algal consortia for wastewater treatment and biomass production.
Okay. Good afternoon, everyone. So I'm Yunglong Luo, and I'm also from Rita's group. So I'm going to talk something different. So I'm going to use cyanobacteria to treat wastewater. So first, I'd like to start with some background information on microalgae-based wastewater treatment. So there are actually some positive characteristics of using microalgae to treat wastewater compared to conventional biological wastewater treatment. So these include the algae have great ability to take up nutrients from wastewater. And they can also capture CO2 from the air. So, and the process does not require a massive amount of energy input. And the biomass produced in the bioreactor can be used to produce biogas, biofuels, and fertilizers. So microalgae-based wastewater can be achieved in two types of systems, open ponds and the photobioreactors. And there's a recent modified version of photobioreactors. We call them membrane photobioreactors. So this is actually one of the research interests of our group. And I'm not going to the detail of this technique, but we have recently published a review paper in this regard. So if you are interested, you can have a look. And as for the algae species for wastewater treatment, so most studies focused on the use of green algae. So cyanobacteria has been much less explored. So is it suitable for wastewater treatment? So actually, cyanobacteria have been frequently detected in wastewater and different wastewater treatment processes. And they are actually more abundant than green algae in those wastewater treatment processes. And they have a number of features, such as high nutrient storage capacity, and they tolerate different kind of contaminants, and they can live together with bacteria. So as part of my research, I want to compare the ability of cyanobacteria against green algae for wastewater treatment or polishing secondary effluent. So the system performance was assessed in terms of different categories, including biomass production, biomass composition, nutrient removal, harvesting potential, and organic character. And we also explored the potential of using polycultures. So we mix different algae together to treat wastewater. So the research is still going on in the lab, so I'm going to show the result we have so far. So these are the photobioreactors we use. We provided them with light, air, and we use a range of microalgae. Two of them are cyanobacteria, as you may see, microcysis and anabina. And we maintain the hydraulic retention time of 1 day and solid retention time of 18 days during the operation. So we use a synthetic secondary effluent for growing algae, and it has a nitrogen of 15.3 milligram per liter and phosphate of 2.4 milligram per liter. So the operation lasted for 28 days, including aromatization phase and the fed batch phase. So I use a range of analytical tools to assess the different aspects of the performance. So let's have a look at the results. So in terms of biomass production, we can see that microcysts did not show very good results. So it was among the least concentrated biomass. And another cyanobacteria, Anabina, was actually among the highest producer. And when we compare the consortia with individual species, and we did not see any improvement in terms of biomass production. And then we use flow cytometer to differentiate different populations. So we can divide them into viable algae, non-viable algae, bacteria, and cell debris. So from the result, we can see that most of the results were quite comparable in terms of the composition, but only the Cyanobacteria showed a much higher percentage of non-viable algae in the culture. And again, consortia didn't show much difference from the individual cultures. And we found that the mixing microcysts with other microalgae species did not cause any drop in the percentage of the viable cells. And we can use the flow cytometer to see the dynamics of the population in the culture. And for in both cases, chlorella was the dominant species in the wastewater. And when we mix microcysts with astigmatos, there was actually a lagging phase after mixing them together before microcysts outcompeted its counterpart. Well, for nutrient removal efficiency, we have some positive result here for microcysts, and it can achieve. It achieved actually the highest removal of nitrate nitrogen from the wastewater, and nearly like 3 times higher than the green algae, Selenastrum. And the phosphorus removal were quite comparable among all the species, and we assume that we attributed this to the high pH in the cultures. They were like most of the time they were higher than 9, so phosphate precipitation could be a main removal mechanisms for the phosphate from the algal cultures. And capillary suction time. So this is a simple measure of the dewatability of the biomass. So it can show how easy we get rid of the water from the biomass. So actually, microcysts produce the least dewatable biomass compared to other species. So it may not be a very good species for harvesting. And another popular green algae show the highest dewatability, which means it will be more easier for us to get water out of the chlorella biomass. And the CST of the consortia was mainly determined by the dominant species. And the CST is also a measure, an indicator of membrane fouling. As I just mentioned, we're going to put the membrane filtration into the system. So I wouldn't recommend using microcysts in the membrane photobioreactors because of the low dewatability. And research also suggested a strong link between biopolymers and dewatability. So we kind of look at the different the composition of organic matter of the of the culture, and they found that microcystis produce the highest amount of biopolymers in the culture, which kind of explains why the biomass was the least dewaterable. So I think so. For my research, I found both strengths and the weakness for using individual species to treat wastewater. And for the cyanobacteria microcystis, it was very effective in removing nitrogen from wastewater, but there are some drawbacks of using these species, such as the low dewaterability, and I wouldn't recommend using it for like the membrane photobioreactor operation. And in terms of microalgae consortia, we didn't see any improvement by mixing like two microalgae together, but we are testing more algae in the lab right now. So yeah, hopefully we can review the impact of like biodiversity in the bioreactors. Okay, that's the end of my talk. Thank you for listening.
Thanks, Yunglong. So do we have any questions for Yunglong?
Hi, thank you. That was very interesting. In using a synthetic wastewater, did you consider using ammonia rather than nitrate as the nitrogen source? Because wastewater would tend to be higher in ammonia.
Oh, yeah.
And also, for either this work or future work, did you look at also adding, if you're going to use synthetic, having a source of BOD? Because obviously wastewater will have a BOD source, and with bacteria present as well, that can then add another carbon source as the bacteria process the BOD and then release CO2.
Yeah, so we actually look at the ammonia as well. So for this type of secondary effluent, we look at those like nitrified effluent. So those wastewater after nitrification. So we tend to have like low level of ammonia. So and in some of my previous studies, I also look at the impact of different nitrogen source on the biomass characteristics. Yeah, so we use both nitrogen source for the wastewater treatment. Yeah.
Yeah, I enjoyed your talk. Thank you. I've just got a question about the growth. You've measured the relative or the growth rates of all the different algae and found that the microcystis didn't perform as well as some of the other species. But I'm wondering, given that you're looking at the use of algae to polish wastewater, whether it might not be better to look at the ash weight of those species, because they're photosynthesizing and accumulating carbohydrate from CO2 in the water, and the aim of the exercise is really to remove all those residual recalcitrant compounds from the water. So microcystis might perform equally well in doing that compared to other algae. So what do you think about looking at the ash weight of just the recalcitrant compounds rather than the total dry weight of the algal cells themselves?
I think we have actually looked at that before. So that is what we call MLVSs in the field of wastewater treatment. So mixed liquor, volatile, solid, suspended solids, and we found quite like consistent ratio between MLVSs, the dry weight, and the ash-free dry weight. So we just compare. So I think that's they offer like similar results for both parameters. That's why we only use one of them. Yeah.
Probably I can't help it. When people are talking about cyanobacteria and toxins and all sorts of things, when we talk about the wastewater treatment plant, why are we introducing a potentially toxin-producing cyanobacteria? And also the environment may very well support. I mean, Microcysis originosa, it's all good to say it's non-toxic. There is no such thing. You know, we have no control over it. Are we playing God here? How exactly we control toxin production when we are purposefully introducing cyanobacteria and providing that environment for that kind of cyanobacteria to grow and be happy? Should we do it?
So there are actually studies looking at the use of cyanobacteria to produce some pharmaceuticals. So they also use some, as long as you can get rid of those toxins before you use them for further applications, I think that's fine. Yeah.
So any more questions for Yunglong?
I just have a comment that maybe what you could do just to make it a little bit easier to compare the species is to put all of them into a matrix so we can see all the values together at the end. So that's just a little suggestion.
Yeah. So we have a lot of more experiments going on. So we'll eventually put them in the big table to compare the results. Yeah.
Okay. Thank you, Yunglong.